Hello and welcome to this presentation on scalable metrics to quantify security of large-scale systems. I'm Sri Balaji, and this is a joint work between Christian Grusler from Technion, and Andre from Uppsala. And this is a presentation created for CDC 2024. The overview of this presentation is I first introduce the problem, I motivate the problem that we study in this paper. I then mathematically formulate the problem. Without going into very much of the technical details, I provide some of the results. I illustrate the results through numerical examples and provide some concluding remarks. So to begin with, traditionally control system consists of a physical process on one side. The outputs of the process is measured with a sensor and it's transmitted to the controller. The controller, like a PI or a PID controller, is employed usually, and the controller generates a control command and is sent to the process. The performance of the controller is usually measured through a performance signal. For example, if it's a temperature control system, the performance signal can be the difference between the set point and the actual temperature. This is like a very brief introduction to conventional control. But due to the advancement of technologies, the wires in conventional control are replaced by wireless networks. And this has been done in physical processor in industrial control system. For example, in a paper production mill in Iggesund in Sweden, there is a network control system using radio signals where they used to control a starch cooker. So here the starch cooker is the plant, and it's basically starch is cooked before it is applied on top of the paper to make it smooth, and the input to the process is temperature, water flow, and the output is starch concentration. Yeah. However, due to the introduction of such networks are not always secure because they can also be legacy networks in power grids, for example. So there has been a lot of attacks on such networks, for example, on the power grids, on water distribution networks, also on physical systems like a car. Uh, and because our control system manage a physical process, there are always physical consequences to these attacks, and IT security design does not always take these physical consequences into account. So we have to design such systems so that the physical consequences of such attacks are very low. So the lesson here is to be proactive and protect the system. Yeah, so what we do is that we take the same block diagram that we had before, where there is a network. However, we consider that an adversary is trying to inject a cyber attack into our network. Yeah, and in order to detect such attacks, we also introduce a detector module into the closed loop. Now, we consider an adversary which is injecting false data. In this paper, we only consider attacks which are into the actuator of the control system. And we specifically consider an adversary that injects such attacks to increase the performance cost. For example, as I said, in a temperature control, it's to increase the deviation from the set point and the actual temperature, whereas the adversary always stays stealthy. So it will never raise an alarm at the detector. Yeah. So this is what we call the impact metric. So impact metric gives you the maximum performance loss or the performance cost induced by a stealthy attacker. Here, by stealthy attacker, I mean an attacker which never raises an alarm at the detector. Why do we need such impact metrics is that once you have such metrics, we put a number on so if you have a closed loop system, we put a number on how we quantify security. So we can use it to design secure systems. So if the impact metric is really low, then we just say that we just imply that the degradation caused by attacks, which are not detectable, is really, really low. That is what we mean by impact. Yeah. And so this paper mainly goes into how do we quantify this impact metric, yeah? And this is something that has already been studied in the literature for quite a while now. However, some of the particular contributions that we bring to this field is that performance loss is usually measured using the induced L2 norm, which is similar to H infinity or LQ control, whereas we focus our attention towards positive systems. And for positive systems, we measure the performance loss using the L1 norm instead of the L2 norm. And due to the way that we formulate the problem, we have scalability advantages. So whenever you have L2 norm, usually the impact, the performance loss caused by stealthy attacks, is given by a solution to an SDP, to a semi-definite program. Uh, However, when we formulate it using the induced L1 norm, we get a linear program to quantify the impact instead of a semi-definite program. Yeah, this is the first advantage. And why is this an advantage? Is because for a semi-definite program, the computational complexity is quadratic in the number of states, whereas for a linear program, it's linear. So if we focus on a power grid where there can be a very large number of states, this can play a significant role on how complexity uh, affects computing the impact. Yeah, and we focus on positive systems, internally positive systems, but we also extend our metric to cone positive systems and also uncertain systems, which I will detail a bit more later. Yeah. So this is the problem that we study in this paper. Yeah. Now let's put some math, or let's introduce the problem mathematically. So we consider a system. So we consider an LTI process uh, where X is the state, Y is the output, and YP is the performance signal. Yeah, this can mean the error. And we, in particular, consider a PI controller. So this is the proportional term with respect to the error, and we consider an integral term. Usually, because here we consider an anomaly detector, right? Usually, anomaly detectors are not readily implemented. So here, what we do is that we take this error signal and we assume that this error signal is available for the operator to monitor. So what we do is that we use this error signal to monitor for attacks. Yeah, that is the setup we have here. So let's assume that the reference signal is zero without any loss of generality. And the input that is fed to the plant is the input generated at the controller plus some attack signal injected by the adversary. Yeah. Then the closed loop system becomes something like this. So the only driving external force is the attack signal. And then you have the performance signal and the detector output. Here, the detector output YR again is the error signal. Yeah, this is the structure of the problem. Yeah, and as I mentioned before, here, just to be clear, we now assume that the adversary and the operator knows these matrices of A, B, and C. Yeah, just to keep things clear. Now, as I mentioned before, we consider an adversary that injects a bounded, again, bounded in the L1 sense, bounded a positive attack signal into the control signal to increase the performance cost while staying undetected. And we consider positive attack signals because we focus on positive systems as well. Mathematically, it just means that the adversary injects false data to increase YP, uh, while YR is below a particular threshold. So the error is below a particular threshold, and the attack signal is bounded for a given bound, and the attack is also in the L1 space, positive L1 space. So if you want to formulate this as an optimization problem, it becomes this. So the attacker essentially solves this problem. Yeah. So just to recap again here, if we solve this optimization problem, we essentially quantify the performance loss caused by positive attack signals that are stealthy, so positive and stealthy and bounded in energy. Yeah, and this is what we call impact metric. So impact is the maximum performance loss caused by attack signal. Again, as I mentioned before, they are useful for analyzing the robustness of closed loop system against attack signal. So this is the optimization problem that we are interested in solving. And in this paper, we mainly focus on two questions: how to determine the value of this problem, is the problem well posed, and is it scalable? And the first result that we present is the following. If we consider this problem and this closed loop system, if this closed loop system is internally positive, then the value of this metric is given by the solution of this linear program. Yeah? This is a linear program. I'm not going to go into the proof of how to convert 6 into 8, but essentially you can prove it using S procedure for infinite dimensional quadratic linear functionals and dissipative system theory for positive systems. Yeah. Uh, and some of the implications of this result is that we get, as I mentioned before, instead of an SDP, we get an linear program. And if the A matrix here is of dimensionality n, SDP grows quadratically, whereas we have linear growth. And in the literature, for example, in this work, impact metrics can be unbounded. So essentially, an adversary can cause unbounded error in your system. However, because of the way that our impact metric is formulated, our metric is always bounded. This is mainly due to the energy constraint of the attack signal. Next, what we do is instead of considering deterministic systems, so up till now, what we did is we considered that the adversary and the operator both had exact knowledge about the process dynamics. Here, what we do is we consider an operator who is uncertain about the process matrix AC. So in particular, we consider a polytopic uncertainty. So we consider the matrix ACL. So this is the actual matrix. The process dynamics follows, and AI are the vertices of a polytope, and ACL delta lies in the convex hull of this polytope, essentially. So it's a polytopic uncertainty. So the process dynamics becomes like this. So essentially, this is a convex set. So this, yeah. So this is the closed loop dynamics for this uncertain system. And the impact metric is given by this optimization problem. So if I focus here for a minute, it's essentially the same optimization problem that we talked about before, but everything here becomes a function of eta. So eta determines where in this polytope your exact matrix lies. Yeah, and everything yp, yr, and a are a function of eta. And you maximize, as you determine the impact metric as the maximum value over this eta. Yeah, so essentially, if you have a set, for each point, so this set represents all possible A matrices. For each given A matrix, you determine the impact, and you go through and you determine the impact for the whole set, and you pick the maximum value. So we determine the maximum performance loss for any given epsilon, for any given eta. So this is the problem that we are interested in solving. And for these problems, what we can again do is that if you consider this type of uncertainty and a closed loop system as before, if this closed loop system is internally positive, then you essentially solve a linear program again. And what we can say is that if the impact for the uncertain system is given by gamma rho, the solution to this linear program upper bounds the impact metric for the uncertain system. Yeah. So if you solve this optimization problem for all given AI, so AI is the vertices of this uncertain set, the impact metric for the uncertain system is upper bounded by the value of this linear program. Yeah, it's similar to, so the proof of this theorem is similar to constructing a storage function, which is like a common storage function or a common Lagrange function. Anyway, we can also extend the results for similar to uncertain systems for cone positive systems. We provide some basic results in the paper, but we do not go into the detail. Some work will come out soon. And for the numerical example, we consider a water distribution system. So here we consider that the operator can measure the water level in tank 1 and tank 2, or only tank 1, sorry. The sense there is a controller and the signal is fed back to the water supply. But this signal, as I mentioned before, is under attack. And the performance of this whole system is measured by the deviation of the water level in tank 6. And the detection threshold is 50. We consider an energy limit of 100, and we solve the optimization problem that I mentioned before. So this is essentially the value of the impact metric. Yeah. This is what we obtain. Now we see some intuitive explanation of this result. So for instance, we consider such an attack signal injected into the system. So here again, see that the attack signal is always positive. And here we represent the error signal is the detection output, right? So it's essentially the error signal. You can see from the plot that the error always is upper bounded by the detection threshold, right? So the black line here is the detection threshold. And because the attack signal always respects this bound, this is a stealthy attack. And here in the third plot, you can see that the black line is the gamma value that I showed in the previous slide. So that's the value of the impact metric. And you can see that the attack signal respects this bound. Yeah. So again, for a stealthy attack, the performance degradation is upper bounded by the value that we found. And this depicts the guarantees also provided by impact metrics. So even though you cannot detect such attacks, the maximum performance degradation caused by such attacks is upper bounded by this value. We also did some comparison to nominal performance. So here I consider 3 acceptable design choices for KP. So this is something that is given to me as an operator. For each of these KP, I choose gamma. I solve for gamma. So this is the impact metric. And here it's the control effort nominally. So when there is no attack, this is the control effort that is required. And this is the performance deviation caused when there is an attack. Yeah. From here, you can see when KP is the largest, the impact is lowest. Yeah. Because also the deviation is the smallest from the reference. So here 0.1 is the reference. However, for such a control design, the control effort is the largest. If you choose KP low, here the control effort is really low and there is no attack. So this is another intuition that such impact metrics provide. So in conclusion, we considered bounded positive attacks on actuator that aim at maximizing performance loss while remaining undetected. We propose an optimization problem that quantifies the impact, and we show that the optimization problem is equivalent to a linear program, and we extend the metric for uncertain and quant-positive systems, and we depict the results through numerical example. Future work includes solving the design problem explicitly. So in the numerical example, I just did an exhaustive search over the available KP. We can also solve for KP explicitly. An extension of this impact metric for other classes of positive systems. Thank you very much.